Swayam Prabha. Digital India. Educated India.
Welcome to this groundwater hydrology course, and we will be delivering this lecture number 31, in which I will discuss about saline water intrusion in aquifers. So, this is lecture number 31, and our main topic is saline water intrusion in aquifers, and topics to be covered under this particular lecture class are occurrence, occurrence of saline water intrusion, second is features affecting saline water aquifers or coastal aquifers. And third one is Bodon, Ghyben, principle. So, first thing, what is this saline water intrusion? What is this saline water intrusion? Saline water intrusion is defined by Fries and Cherry as the migration of salt water into fresh water aquifer under influence of groundwater development. So, this is basically defined as migration of saline water into fresh water aquifer under the influence of groundwater development. So, sometimes we use this groundwater word as single word, however, in this particular course we are using separate words, groundwater. So, what is this influence of saline water effect in freshwater aquifers? If we see our coastal aquifers, then you will see that, let us say, we have one pumping well, which is pumping fresh water from, or which is drawing fresh water from the coastal aquifers. Another one is the well which is already contaminated. So, if we see, this is our effective so we have groundwater table located here, and this is our ground surface. So, this particular well is pumping fresh water, and this one is pumping contaminated water. This is our sea surface, or this is your sea, and basically this is the position of salt water, and this is our original interface between salt water and fresh water aquifer, and this is our location for fresh groundwater, and this is salt water, and this is our interface location. So, there will be exchange of fresh water and saline water in this region. Due to pumping, there will be effect of pumping within our coastal aquifer, and there will be lowering of groundwater table or GWT in this region. So, this is basically a typical coastal aquifer, and in which due to pumping effect there will be contamination due to salt water. And now, we will try to discuss what are the features or what are the occurrence, what are the possible reasons for occurrence of saline water intrusion. There are three mechanisms which are responsible for occurrence of saline water intrusion. First one is reduction or reversal of gradient. General perception is that there will be flow from freshwater aquifer towards the sea, but when we have higher pumping case in the freshwater region, there will be reversal of gradient in that particular case. Second one is this is basically destruction of natural barriers. Destruction of natural barriers, this is another important reason for saline water intrusion. What are these barriers? Maybe we can say our Sundarban region, we have mangroves, and destruction of mangroves can cause saline water intrusion in this coastal region. Third one is totally human intervention, and this is due to dumping of saline wastes. This is due to saline wastes, and due to this saline waste it can cause inland salinity, or near the region of the coastal aquifer it can cause some kind of extra effect of salinity near coastal aquifers. So, now we will try to figure out the features which are affecting saline water aquifers or coastal aquifers. Saline water aquifers or coastal aquifers. So, first one we can say this is due to human activities. Human activities. What are these human activities? First one, we can say that groundwater extraction. Second one is mining of gas and oil. Second one and is mining of gas and oil. Third one is lowering of groundwater table, and fourth one we can say that human saline wastes. So, what is this groundwater extraction? What is this groundwater extraction? Let us say that we have some city well field which is drawing water from the nearby coastal aquifer, and this is our ocean, and this is saline groundwater, and we can denote this thing as fresh ground water. So, what is happening due to this is our GS or ground surface, and this is again groundwater table. What happens due to constant pumping from city well field, there will be a gradual movement of this interface towards this wells, and finally, if this well these wells draw significant amount of water from this freshwater aquifers, it can cause saline water intrusion in groundwater aquifer. So, we can say that pumping is a responsible point for saline water intrusion, or an important feature for this effect in freshwater aquifer for coastal regions. Second one, we talked about this mining, gas and oil. So, most of the cases we see that mining operations are usually carried out near coastal regions, that can affect significantly our fresh groundwater aquifers. Third one is lowering of groundwater table. There may be different causes due to which there can be lowering of ground water table. And another thing is that human saline waste, that can also cause saline water intrusion in coastal aquifers. So, if we distinctly see different things. So, for unconfined and confined aquifers, for unconfined aquifers, we can have different situations. First one is your bed condition, which is impervious in nature. Then this is sea level, and natural recharge or natural recharge is occurring from the top. This is our groundwater table or GWT, this is our GS or ground surface. So, this is common thing that there will be movement of water from freshwater aquifer, and this is basically our interface location. Second case, if we have some kind of confined aquifer situation, this is again impervious, this is our sea level, another impervious region, so this is the location of interface. This is for unconfined and this is for confined aquifers. Again this is groundwater table and this is ground surface. We have fresh water here. So, these are two examples for interface movement in confined and unconfined aquifers, and we can say that this is our piezometric surface, for unconfined confined aquifers. Another situation we can have, that is island situation, that is for island aquifers. Freshwater, interestingly for island aquifers we have a different setting, in which on the top we have fresh water and from the bottom we have this saline water, and this is our normal groundwater table. And in islands only source of water or fresh water is natural recharge. Natural recharge is the only source of water. So, these are for unconfined, confined and for island aquifers. In these cases we have considered a sharp interface between our fresh water and sea water or ocean water. In reality, this sharp interface does not exist. This is basically our one kind of approximation to real world problem. What exists in reality is some kind of diffuse interface. In fresh water we have less density, and in case of sea water we have high density. So, there exists some kind of density gradient between this fresh water to sea water region, and in between we will have some kind of diffuse region or diffused interface position. So, we can say this region as transition zone. Transition zone, and this existence of transition zone is due to molecular diffusion and dispersion process that occurs during mixing of seawater and fresh water. So, what is this thing? So, like previous figure, we will draw same So, this is our sea region and this is our phreatic surface. This is fresh water and this is saline water. In between there exists something that is called transition zone. Thus, density of fluid within this transition zone is in between saline water and fresh water. So, next thing or next point for this features affecting our saline aquifers is coastal zone effect. In coastal zone effects, we have coastal coastal erosion process, next is shoreline retreat and tidal effect. What is this coastal erosion? Due to decrease in the number of mangrove trees in this coastal regions, or we can say this coconut trees, there is some kind of coastal erosion occurs in the coastal shoreline, and due to that coastal erosion is one important thing that affects our saline water intrusion in coastal aquifers. Next one is this shoreline retreat. Shoreline retreat is a common problem, and one example of this is Cape Hatteras, this lighthouse in US that has been shifted towards inland somewhat 2,870 feet, 2,870 feet inland due to this shoreline retreat effect. And third one is tidal effect. Tidal effect or wave effect. This tidal effect or wave effect is generally generated due to water waves, and during tsunami or high water wave or natural tidal fluctuations, there will be some kind of effect within the coastal aquifers. So, what are the influencing things during this process? So, this is again our groundwater table and this is our land region. So, land region we have this overland flow and from ocean we can have some kind of wavy effect due to this tides. And for this freshwater thing, next we have some kind of, let us say, some kind of aquitured region. And finally, this is base, some kind of impermeable base. This is our confined aquifer and fresh water comes from some upstream side. This is our aquitured, this is our base. So, there will be intrusion of brackish water and there will be interaction between fresh water and this brackish water. And flow is generally towards sea. So, what are the other things we have? If we denote C as convection, H as hydraulic head, T as tidal pumping and W as wave setup, then we can show that there will be discharge from the fresh water towards the sea due to these four components. One is directly, this is wave setup. Next one is due to hydraulic head and we have this tidal effect which is occurring near to this interface between aquifer and sea, and our convection process that occurs in this brackish water, or in this region brackish water region, and also some kind of tidal pumping setup that occurs in this region. Similarly, for confined aquifer, this is our unconfined aquifer and this is our confined one. So, in this brackish region again we have convection which dominates the flow conditions and tidal thing which dominates the flow condition near brackish region, and this is governed by the hydraulic head. So, next feature that is affecting saline water intrusion is sea level rise or rise in sea level. This particular point is somewhat debatable point, because some people have negated the effect of sea level rise for seawater intrusion in coastal aquifers, but sea level rise significantly affects the salt water intrusion near to coast, only near to coast. Its effect may not be that much inwards or landwards region, but it is surely affects the region which is near to shoreline. And what are the sub points under this? This is one is global warming, which affects sea level rise and it is indirectly affecting salt water intrusion. Next is land subsidence. Due to land subsidence, there may be sea level rise, and also due to some kind of tectonic uplift. Due to some tectonic uplift, there can be rise in sea level. So, next point is changes in hydrological or geological regime. Hydrological or geological regime. Individual points we can discuss under this thing is changes in natural recharge, changes in natural recharge. Next is evaporation. So, what is the effect of changes in natural recharge? There may be reduction in rainfall pattern or increase in rainfall pattern that can affect our sea level this salt water intrusion. Next one is evaporation. Due to evaporation, water there may be concentrated amount of salt may be available near the creeks or any other region near to the coastal aquifers that can cause salt water intrusion. And third one we can discuss, that is sea water entered aquifers during past geologic time. So, seawater that has already entered in the lower aquifers or deeper aquifers during past geologic time, that can significantly affect our inland salinity part, inland salinity or near to the coast also. Sometimes what happens, due to different kind of stratification, your fresh water may be at the lower strata compared to the sea water, which is at the topmost strata due to some effect, or we can have situations where this sea water is located in the deeper aquifers due to some geological event in the past. And last point under this particular thing is effect of river and estuaries, river and estuaries. One point we can say, that is backwater effect, salinity of surface water, and final thing is seepage. So, what is this backwater effect? Due to this rivers which are connected to the sea, there may be backwater effect, and due to tidal variation it can affect a significant portion of the river, and in turn this salinity of surface water can cause saline water intrusion in coastal aquifers or inland aquifers, along with other effects like heavy extraction or heavy pumping from this particular aquifer. And seepage is another reason for saline water intrusion. So, if we summarize this features that are affecting our saline water intrusion, then what are the effects or problems due to this saline water intrusion? First one is loss of drinking water, loss of drinking water. Next, due to loss of drinking water, there will be problem in related to habitat. Next is increase in soil salinity. Due to increase in soil salinity, there may be problem related to agriculture. Third one is possible relocation of habitants, possible relocation of habitants. This is another important point. So, on the whole, serious consequences on environment, ecology, and economy of that region. So, sorry, these are the effects due to, or these are the problems due to saline water intrusion in aquifers. So, next point we will discuss about this Bodon Ghyben Herzberg principle. So, this is the most simple approximation of the interface for modeling the saline water intrusion in coastal aquifers. So, what are the inherent assumption for this particular principle? First one, assumptions. First one is that the aquifer is homogeneous. Next one is hydrodynamic dispersion is negligible. Third one is that vertical, the third one is that saline water, saline groundwater is at rest. Saline groundwater is at rest. So, to derive this thing, we can use our hydrostatic principles of fluid mechanics, and we can directly employ those pressure related relationships for derivation of Bodon Ghyben Herzberg principle. So, first we can sketch our geometry. So, that is, this is our ocean, and we have interface like this, and this is our impermeable base, for this problem. This is ground surface, this is groundwater table, and this particular location we have our z axis, this is our x axis. So, this depth from the sea level we can denote it as x y, which is a function of x and y. Again, this depth of interface, this is as x y, and from the ocean surface to our groundwater table we have H f depth. So, this is our interface and this is our salt water, and this is the location of toe, and we have impermeable bottom. So, from this one we can write that H s equals to rho s g plus z, and H f equals to p rho f g by z, where rho s is the density of salt water and rho f is the density of fresh water. So, during dynamic equilibrium there should be pressure continuity at the interface. So, what we can do, we can equate the pressure from these two equations, and if we equate the pressure from these two equations we can directly write H f rho s H s plus rho s minus f. So, what is this? This is calculated from the x axis, and this is the depth of this location. So, basically our function is minus z. So, we have replaced this minus z with this thing. Now, if we equate these equations, then we will finally get rho f by rho s minus rho f into H f H s rho s rho f and H s. Ghyben, Hausberg, they have further simplified that the salt water is stagnant. Salt water is stagnant, thus we can directly use hydrostatic principles, and rho s g we can directly write it. So, further from our previous equation we can write that rho f by rho s minus rho f into H f. If we consider our rho f equals to 1 gram per centimeter cube and rho s as 1.025 gram per centimeter cube, then we will see that this value is approximately 40 times H f. So, we can say that for every meter of fresh water above mean sea level, the thickness of the fresh water lengths resting on salt water is about 40 meters. So, we can see that for every meter of fresh water above mean sea level, the thickness of fresh water lengths resting on salt water is about 40 meters. And for this Ghyben-Herzberg principle, it is mandatory that you should have some depth above mean sea level, otherwise there will be reversal of flow from this region. So, we can say that this is one important historical development for saline water intrusion measurement, and it depends on sharp interface principle. So, today's lecture we are concluding with this Ghyben-Herzberg principle. Next lecture we will discuss the application of Ghyben-Herzberg principle for identification of saltwater intrusion in coastal region. Thank you.